Hello, everyone. In a lecture, when I proved that the Bergman space is complete, and in the videos where I did the same thing, in Introduction to Banach spaces at about the 45 minute, 40-second mark, I stated that if you have a sequence of holomorphic functions on the unit disk, or really in any holomorphic over any open connected set, that is uniformly Cauchy on each compact subset K of the disk, then that means that you have uniform convergence on compact subsets of Fn to a holomorphic function. I said in lecture that's Morera's theorem. So I must have seen it in a book that called that Morera's theorem. It's really a very easy consequence of what is usually called Morera's theorem. So I want to state and prove that as a lemma, because why not? Why not? And I also want to introduce the Hilbert Hardy space in this video. So let me get out of here. Okay. So this is from Stein and Shikarchi. So this is what they and most people call Morera's theorem. It's really the converse of Cauchy's theorem. So if you have a continuous function on an open disk, such that for any triangle contained in D, the integral is 0, then f is holomorphic on D. Okay, so often this is stated in terms of a little less general. If for any for all closed curves within D, the integral is 0, then it's holomorphic. So this is a little easier to check. So yeah, let's use this to prove what we used in the video and what in the lecture I called Morera's theorem. Right, so it'll be pretty quick. It's a really easy application of Morera's theorem. So call it a lemma. Let's say this is a subset of holomorphic functions satisfying the following condition, which I called before uniformly Cauchy on compact subsets. So for any compact K, any epsilon bigger than 0, there exists n, depending on, usually for uniform convergence, it's just epsilon, but here there's no claim of uniformity for each compact subset. It's just for each compact subset there is, and for each epsilon there is an n, where the following is true. This implies, well, Fn basically is Cauchy in a sup norm over K. There's technically nothing wrong with X, but it's a little weird because we're in the complex plane. Let me get rid of this. So, sorry, I just got rid of a PDF. Okay. Then there exists F holomorphic. Where this is true, uniform on each compact all right, so let's see how to prove this. So let's call this star here. Lack of anything better to call it. So one kind of trivial thing to notice is that for any point in the disk, there's a compact subset of the disk containing that point. So you in particular have pointwise Cauchy for any point in the disk. So in other words, for any Z in the disk, this sequence here of complex numbers is Cauchy. So let's denote the limit by f of x. And we're actually even almost done. This is not a terribly deep result. Okay. So yeah, all we're saying is this is Cauchy, hence it converges as a complex number. Let's say f of z is this limit, which we know exists. Okay, so let's prove uniform convergence on compact subsets. I claim that this is uniform okay, why let's say epsilon is bigger than 0. Sorry. Let's pick K compact. So pick N from star, which is from right here. So pick N where this is true. Then N bigger than N implies the following. And Z is in K. So I'm going to show directly, I'm going to show directly we have uniform convergence. Okay. So pointwise f of z is this limit. So just as a complex number, as a non-negative number, just properties of limits, this non-negative number is equal to this limit. And this is less than epsilon. Implicitly, m is also bigger than n because it's going to infinity. So that's just from star. That's literally what star says. As long as z is in k, this max is less than epsilon. Okay, so the conclusion is as follows. So I mean, a priori, or initially, we don't know that f is continuous, so we can't really say max. Whereas I use max here because everything's continuous here, so the supremum is a maximum. So I'll just use supremum. Z and K. In particular, this big N only depends on, remember, it depended on epsilon and K. Again, no claim of uniformity in all on K or for all K. For each compact subset, we have uniform convergence. Big N most certainly in general will get larger as K fills in more of the disk. But in particular, this does not depend on Z and K. Okay, so we have carefully proven that we have uniform convergence on K. Okay, and in particular, F is continuous on each compact subset of the disk. So obviously, it's continuous on the disk because it's continuous on each point in the disk. Okay, so now we can use Morera's theorem, okay, to prove that F is holomorphic. And I'll just use the Stein and Shikarchi. Any version of Morera's theorem works. So if this is a triangle, clearly this is compact. Closed triangle when we say triangle. So by uniform convergence of Fn to F on T, we have that this integral here, and this is often a typical use of Morera's theorem. It's a uniform limit of holomorphic stuff. And by Cauchy's theorem, you know that you integrate over any closed curve in your domain. Here's the disk, and this function is holomorphic in that domain, and here's the disk, then that integral over that closed curve is 0. Okay. So that implies F is holomorphic on D. So really an easy complex analysis homework type problem using Morera's theorem. Yeah, so this is Morera's theorem. Sorry. And as I said before, this is Cauchy's theorem because Fn is holomorphic. I don't know why this is so slow on Zoom. And this is, remember, just uniform convergence. Not K, but T. Okay, so yeah, if that seemed a little mystical in the video or in lecture, kind of why I call this Morera's theorem and how you prove it, then hopefully that made a lot more sense. Okay, so let me quickly introduce the Hilbert Hardy space. So big H for Hardy. Same Hardy from the movie on Ramanujan. Same Hardy that does a lot of number theory, Hardy little word maximal function. Yeah, super famous like mathematician, G.H. Hardy. Okay, so the Hardy space is all it's sort of like the sort of like this unit circle version of the Bergman space. Explain what I mean by that in a second. So it's all holomorphic functions on a disk. So it's holomorphic, so it has a power series expansion. And the condition is that this is square summable. These Taylor series coefficients. So it's got a little funky norm, inner product. So this is going to be the following, and we'll compute this in a second. And we'll show that this is the Hilbert space, is a complete inner product space. Okay, so a little proposition is as follows. F and G are in the Hardy space. And let's say G, let's use the coefficients Bn on the disk. So I claim that this is actually an incredibly simple inner product. And the proof is, let's just compute this. Basically, we're going to compute this limit here. So forget about limits for a second. So let's look at this here. So it's this infinite sum here. It's a product of these two. I'll use n and m. So plot this into it's z to the n, so it's r to the n to the I n theta. And then do the same thing for g. Remember, g is this power series expansion on the disk. but it's complex conjugate, so it is going to be, certainly would not be true without a complex conjugate. So complex conjugate for the e to the I m theta makes it a minus. Stick a d theta there. So remember, hopefully you remember this. It's just e to the minus I m theta. Okay, so I'm fixing, maybe to be clear, fix something between 0 and 1. Okay. So we have uniform convergence of both of these infinite sums. In terms of theta, because r is between 0 and 1. That's just the Weierstrass. I mean, that's just because, yeah, or rather, sorry. Yeah, both of these r e to the I theta is in the disk of radius r, center 0. And because r is less than 1, we have the closure of that disk is contained in the unit disk. So we always have uniform convergence of a power series on a disk whose closure is contained in your open set. Okay. So, and both of these are finite, are bounded on the disk of radius r. Because again, the closed disk of radius r is contained in the unit disk. So we have the product of uniformly convergent series. They're both bounded, but in general, as long as one of the series is bounded, then that's enough for the product to uniformly converge. Okay. So yeah, so by uniform convergence of these power series on the disk of radius r, center 0, because again, r is strictly less than 1, we have the following. And I'm pulling out limits because we have uniform convergence. So let's use, big N. So it's little n equals 0 to big N, a n, r to the n, e to the I n theta. Same thing. M equals 0 to big N. Make that a little neater. Really ugly summation. So M equals 0 to big N. Bm r to the m. You should probably see where this is going. So yeah, we'll worry about letting r go to 1 later. Right now, it's not really relevant. It's not, just fix an r between 0 and 1, so we get uniform convergence. So I'm going to write this as one sum, and it's a finite sum, so no issues interchanging sums and integrals. So this is going to be just combine everything, and I forgot complex conjugate here. Sorry about that. You need that when you take the complex conjugate of G. So it's ANBM complex conjugate. Make my screen a little smaller. Fine. R to the N plus M. And last but not least, E to the IN minus M theta. Okay, well, really, I could really just pull the integral here, so might as well do that. Okay, and this is an integral you've seen a million times in complex analysis, hopefully. It's 2 pi if n equals m, 0. Just integrate this. If you really want to write this in real and complex parts and then integrate, and you can see this is true. If n is not equal to m, it's 0. So let's just use the letter n. Oops. Whoops, also, this should have been a big N. So like that. Okay, now I'll just write it as an infinite sum. So it's A to the N, B to the N bar, R to the 2 N, and yeah, and I forgot forgetting a lot of things here. Forgot the 1 over 2 pi. Right, so 2 pi's cancel when n equals m, so this is literally what this is. So this equals this. So note that by the Cauchy-Schwarz inequality, this is absolutely convergent. There's no issues whatsoever, in particular because AN, the sequence, and the sequence BN, they're both in little L2. They're both square summable. All right, so to finish this off, no, actually, I did not forget that 1 over 2 pi. That cancels out this one, so there is no 2 pi, 1 over 2 pi here. Sorry about that. It's a little late in the day, so. All right, so an easy exercise that you should be able to do. I claim that the following is true. This will finish the proof. So you can't just willy-nilly interchange limits and sums. I mean, if you're familiar with the general dominant convergence theorem, or just general measure spaces, then yeah, if you just have counting measure, then this is just dominant convergence theorem. But you should be able to do this directly without without any recourse to dominant convergence theorem. I'll do that in a second. All right. Pick a big N where the sum here where this is less than epsilon over 2. Okay, so I want to look at this minus this and prove that for r close to 1, this minus this, an absolute value is small. Okay. So this, of course, I want to bring it under one sum. It's the only thing that makes sense. Second. Okay, so this equals, or yeah, I'll do it equals and I'll smash in absolute values in a second. N equals 0 to infinity, an bn bar r to the 2n minus 1. Okay. So smash in absolute values. You don't really need absolute values. R is between 0 and 1, so this is 1 minus r to the 2. Okay, so let's do I'll do a less than or equal to in a second. Not going to rewrite it, but so let's do 0 to big N. Plus a term we know is less than epsilon over 2. Okay, well, certainly 1 minus r to the 2n, even if r is not close to 1, this here is less than or equal to 1. It's between 0 and 1. Okay, so I can make this a less than or equal to and just do away with this. But this we know is less than what we just had here, epsilon over 2. Yeah, again, this is when we go from 0 to infinity in this sum by Cauchy-Schwarz, we're assuming the sequence an and the sequence bn is in the little L2. So this is when n goes to 0 to infinity, the sum is convergent. So it's just tail of a convergent sum. Okay. So this is less than or equal to epsilon over 2 plus the sum here. Oops. And we're basically done. Because this is a finite sum. Just standard limit laws apply. So let me call this whole thing star star. So pick Use standard epsilon delta language. So it's a one-side limit, so yeah, sorry. So yeah, pick delta where this is true. So R is really close to 1. Implies this is less than epsilon over 2. And this delta works then. Okay. So if this is true, then we're done. Okay. That implies the following is less than epsilon. So yeah. Like I said, really do not need dominated convergence theorem or anything fancy whatsoever to do this. Thanks to the fact that the sequences AN and BN are both in little L2. All right, so that finishes the proof. Okay. So we really haven't talked about linear maps between norm vector spaces. If I did, I could say that this Hardy space is isometrically isomorphic to little L2, and then clearly is therefore a Hilbert space. But yeah, I haven't talked about anything like that yet, so it still should be pretty clear that this is complete. So let's say Fn, this is very, very quick. So all of a sudden, a pen and pad, digital pen and pad is working better. It's weird. So yeah, let's say this is Cauchy. So if Fn of Z, let's use K. Okay. Then what this says is so if we have yeah, so let's say AN is a N1, AN2, etc. So this whole thing here is something in little L2. So one thing in particular is that this says that the norm on my Hardy space is basically given by the little L2 norm. And the reason is just yeah, I'm not going to write it, but clearly this says that the L2, the H2 norm of F, the doing F inner product F, is the little L2 norm of the sequence AN here. Not to be confused with the sequence index N here. Yeah, so this equals the little L2 norm AN okay. This follows exactly from what we've done. Okay, and this is a very easy proof, but so let's say A is this limit here. Oops. And I'm using the fact that we proved that little L2, little LP we proved is complete. So A yeah, sorry. So let's say this is this limit here. So if we define F to be, let's say A is A1, A2, etc. is in little L2. So if F is the following, let's use K. And remember, each one of these is an element in a little L2. Sorry, I want the sum. So finally, this here. So again, the norm of F minus Fn is just the what we've proved is the little L2 norm of A minus AN, the limit, and that's just 0. So Fn converges to F in the norm of the Hardy space. Okay, and that proves it. Okay. Okay, so yeah, next up is starting to carefully study Hilbert spaces. We'll talk about the nearest point theorem, talk about orthogonal projections and all that good stuff. We'll use the Hardy space and the Bergman space as examples, really nice examples that you can really concretely compute things with. So yeah. All right, so long, take care. Bye-bye.